Hello, everyone, and welcome back to another session on critical thinking. Today, we'll talk about problems of induction, and we'll start thinking about scientific method and the whole complex subject of how to think like a scientist and what does it mean for us, and also more than that, what does it mean for uh, us as human beings, not just scientists. So I'll try to explain. Um, what I mean by critical thinking and scientific thinking. And as you know, my methods here, I will not teach you anything. I can only tell you what to think, and you come to your own views and conclusions. So that's what Socrates said, and I will hope to follow in his stead. So I'm not really teaching here. A lot of this information is sort of available in various books, and I hope that my lectures are letting you um, come your own conclusions in any of these subjects. But first, I think let's talk about a few logical, um, let's say, uh, arguments that we didn't touch in the last lecture. So one thing we didn't really touch when we talked about the various types of arguments is whether the arguments are necessary for something to be true, or sufficient something to be true. There's various sort of statements here that uh, kind of make things necessary. As an example here, I'll say, if I say my smartphone needs to be charged in order to call you, yeah, is that all that I need for me to call you? Probably yes, but will I still call you? No, because there may be cases where my smartphone is charged, but I will still not call you, right? That's why you say that there are necessary conditions in the argument, yeah, for something to be true, but it's not guaranteeing the truth of the statement, because I may still not call you. However, if there's several necessary conditions together, and if one condition is met and the second condition is met, and there's no way out of it, it's kind of like in a deductive logic, if one follows from the other, you must do that, then it will call, let's call it sufficient. So there are sufficient conditions. So if one met these conditions, guarantee the truth of the statement. So if I'll say, okay, if I purchase and have the smartphone with me, it is a sufficient condition to call me a smartphone owner. Yes, I own a smartphone. I paid it for it, because I paid for it. Then it is really a condition now to call me owner. Now, if I were turn it into a discussion about calling you or not calling you, the lots and lots of other necessary conditions that have to be met, it's very difficult to say what's sufficient. It is almost hard to come up with a airtight scenario that I have my smartphone with me and I'll call you 100%, because there's so many things could happen. I don't know, there's gonna be an explosion, and I will not be able to call you, or uh, the phone connection will go bad, I won't call you. So yes, but a very simple act of purchasing and having a smartphone with me will still qualify me as a smartphone owner, so that's a sufficient condition. Yeah. There are lots of other things that people call logical fallacies in the arguments, and I will touch on that in the next series, or one of the series. We will talk about various logical fallacies, errors. We'll discuss today, a simple one, which is kind of the affirming the consequent. And sometimes the arguments, they are all kind of valid forms, but they just not necessarily follow that there is, they have truth in them, right? So for example, you could say one type situation, say, and you call them sort of if A then B, and what happens if you have A? Well, therefore B. So it's kind of a deductive argument, and it thinks very simple. So if a person, say John, doesn't finish his homework, he will not go to class. He doesn't finish his homework, so he doesn't go to class. Perfect. It's as simple as can be. However, if you revert that and you say, well, if A, then B, and B happens, therefore it's 100% A, that is affirming the consequence. So, for instance, if John doesn't finish his homework, he will not go to class. Now, he doesn't go to class. Does it necessarily follow that he didn't finish his homework? No, he made go to class because he got stopped because the alarm clock didn't ring, or maybe he was late. He was stuck on the bus. Generally, the weather in the city was so bad that he couldn't get to school. Many things can happen. So obviously, that is not a valid argument. Now, or maybe a valid argument. I'm sorry. It may not be may have a structure of valid argument, but it doesn't have a truth in it. Yeah. Then let's go back to a situation when it's sort of reversed here. So if A then B, and it's not A. So let's say, well, if our team wins tonight, there will be a party in town. Our team doesn't win, and there's no party. Yeah. Okay. That on the surface of it looks excellent, but also can have a problem with it because, well, there may not be a party in town just anyway. Even if our team didn't, win tonight, there was no party in town. It really doesn't follow that there shouldn't be a party in town just because we didn't win. And even worse than the argument in the upper corner here says if our team wins tonight, there will be a party in town. There was no party in town, and team didn't win. Well, maybe they decided to not have a party in town. So it's not an airtight argument as well. So out of those arguments here, maybe only the very simple deductive argument in the lower left corner is an airtight one. I mean, a typical here says, well, I have fever, yeah? Well, I have a fever, then I have a flu. Okay, you affirm the consequent is true. And you're also inferring that, another premise is true. But now the premise that every fever, what is actually implying here, what is implied here, that every fever is the flu. Well, is there every fever a flu? That, you don't know, probably not. Your experience says that's not true. For example, you can describe a situation, a world which, I don't have a flu, but I have a different reason for the fever. Yeah, I mean, there could be lots of things. So you see that argument is not correct. Okay, so it's just a few examples of these kind of various fallacies that can happen with deductive arguments. But let's go back to main discussions we're going to have tonight, which is about the scientific method, and remind you of what is deduction, induction, and abduction truth. And deduction deals with obvious truth, and that's basically the original Aristotelian logic, examples of which I just showed you, and lots of this is kind of complicated. Has complicated Latin names for various arguments. Great stuff, right? But it deals with obvious truth, and it goes from sort of general principle to a special case. And as I told you last time, that's what kind of sits behind the logic and sits behind the mathematical logic, and then eventually that's what feeds our computers and artificial intelligence. It's deduction, yeah, part of it. So if A then B, it's all kind of airtight. Great. Now, when you go to the inductive logic, then you look to the future compared to the past, and you go from a special cases. You say, well, if this is the case, then you can build general principle from that. However, it doesn't deal with certainty. There's no certainties here. Yeah? It's only probabilities. But I'll demonstrate how inductive logic has a problem, which deductive doesn't. And then the abduction, which is basically a scientific method, is inference to best explanation, when you don't select just one, but you kind of search through various inductive um, logical arguments to come up with a best explanation. And that's what Sherlock Holmes says. When you eliminate the impossible, whatever remains is the truth. Now, say it must be the truth, and then you can argue with that. Must it be the truth or not? So now it's very interesting to compare this statement with Occam's razor, and Occam's razor is an example here. You can see here is the principle. Then when choosing between explanation, the simplest one is obviously the best, usually the best, yeah. And where things are requiring more assumptions and more complexity, that is less likely to be true. Yeah. So a little bit about the fact, well, if you hear the hoofbeats, that means what? Are you likely to hear, if you are in the middle of England, say, and you hear hoofbeats, or say here in the middle of the field in England, hear hoofbeats, you're probably more likely to see horses around the corner than zebras. So, and it will require you fused assumptions, because if you can make an assumption, okay, yeah, I may have zebras here. Maybe there should be a safari park nearby, or maybe the zebras ran away from the zoo, and that's I'm gonna see them. But it's more likely that you have horse race nearby, yeah, or something like that. So it is actually very simple, logical inference. Yeah. Now, when you sift through various explanations, which one is the simplest? So you'll have to eliminate a number of them, which means when we get back to Sherlock Holmes' dictum, saying that you've eliminated uh, the impossible, whatever remains must be the truth now, even if it's improbable. Is a little difficult to say, well, is it the simplest explanation? And it is actually not necessarily true that the simple explanation is true as well. So Occam razor is good, but it doesn't mean that you should stop and accept your first explanation as final, because there might be even better explanation. Yeah, a good explanation of some evidence is not necessarily a good explanation for all evidence. So you have some evidence, but let's say you are not in the middle of England, or you're actually in the middle of African savanna. So obviously the best explanation there is zebras. Or even if you were in the middle of England, maybe you didn't know a fact that actually there was a escape from the zoo, right? And indeed, that is true that the zebras escaped, and you're going to see them around the corner. So, hey, you have to accept all an explanation. You'll have to have a high degree of confidence that there is a simple explanation, and you just know all the facts. And this is where the problems with the experience come in, because you've relied on experience and using the Occam's razor. But actually, Occam's razor just says, well, that's the simplest explanation of what you know to be simplest explanation, what you know to be generally true from your past experience, yeah? But that past experience is based on that inductive logic. And the best an inductive argument can do is really to suggest that things are likely. It is likely that you're going to have horses. If you're in a country that has a lot of horses, and it's just a generally normal thing to see them. So it's quite a reasonable explanation. And you work from past experience. You've seen horses before, so it's unlikely that zebras are around the corner. But what if the past experience is wrong? So a very simple explanation here, say, and that's something that I think was suggested by English philosopher David Hume. There's a lot of quotes around that, but say that is, it's a normal inductive problem. Yeah, every day for millions of years the sun has risen, and thus the sun will rise tomorrow morning in the usual place at the usual time, for this day. That is a true statement, in inductive sense, true statement, but it is not 100% airtight statement. And we'll talk about Thanksgiving turkey problem, and you will see how that is not true. So in all circumstances, so it is probably true that the sun will rise tomorrow, but it's not a deductive truth. It's not an absolute truth, because the world may stop. So you would find out that many things we take for granted are not necessarily the truth, and we really underestimate the uncertainties. Now, in the case of sun rising in the horizon tomorrow morning, the uncertainties are exceptionally small, because you've run so many trials during this history. You probably know very, very, very precisely that they follow not random path, but a law of nature, and it is extremely, I mean, it's not even extremely likely, it is 100% almost infinitesimal possibility, really infinitesimal possibility that it will not rise tomorrow. But still, in sense of logic, it is not 100% true. Now, lots of other cases when and where this is going to be more difficult, that problem of induction, and we'll deal with it later. It allows to avoid sort of misleading methods that simply inform seeking confirmation. Yeah. And instead you'd say, well, okay, if I have a problem with my past experience, I'll have to test it more and more times. Obviously, sometimes you will have to accept something as true, and you will have to look at how to falsify it. And the biggest sort of falsification here is a black swan problem. Yeah, it is a black swan problem that is really hit home recently. The most important, sort of most visible one that we know about is COVID-19. It's a classical black swan problem. But the philosopher and author Nassim Taleb was writing his book about black swans after, I think, the 9/11 crisis and 2008 economic meltdown that nobody expected, and it sort of came in handy. I think this was talked about before, but he kind of started really naming that phenomenon of the induction, problem of induction. And what it is that for years and years, for centuries, it was an acceptable and inductive truth that all swans are white. However, when European settlers ended up in Australia, and then they saw that for the first time, they saw that the swans are not all white and they're black swans in Australia. That's inductive logic was falsified. A century and a half later, English philosopher John Stuart Mill then used that bird example to demonstrate it. So it said no amount of observation of white swans could allow the inference that all swans are white. But there was an observation of a single black swan, and it was sufficient to refute the conclusion of years of human experience. Years, and it's just basically dismissed it altogether. So it only takes one counterexample, and then you falsify that inductive line of reasoning. So the black swan events defies kind of previous experiences and expectations. and it's really impossible to predict. Now, it kind of comes to our logical discussions and later on when we talk about probabilities. But it is impossible to eliminate a possibility for black swans. I've read it in many books. Obviously, I read Nassim Taleb's and then read a recent book on called Radical Uncertainty, which I'll also introduce here. I mean, it's sort of implied in the scientific thinking that, you know, theories would be falsified, right? But it always takes us aback. It always strikes us in the face of something unfair, that there are black swans that you didn't expect. It's unknown unknowns, which, you know, a famous phrase uttered by Donald Rumsfeld. But it is so true. And unknown unknowns are impossible to know. You can get, you know, your knowledge perfect in some ways, but because, you know, human cognition is limited, you would never actually attack all sides of the problem, and then another that black swan appear in front of you. So given that it cannot give you an absolute certainty, that inductive reasoning, the most valuable kind of reasoning, would be almost not to seek confirmation, but invite falsification. So that means you probably have to invite criticism, you know, introduce alternative models and look at which models are possibly also could be possible, right? You will never actually get rid of your most likely model, right? You will still try to seek confirmation because it's on our human nature. We'll talk about confirmation bias later on, but it's a good practice that you should seek falsification of what you do. And great falsification test is a Thanksgiving turkey test, or for Muslims here, say it's a lamb test before Eid al-Adha. Also by Nassim Taleb, I think there was another author who also mentioned this, but you know, it's sort of you know, flies in the face of the observational science, right? So imagine you are a turkey and your job is to create projections from your quality of life. You start kind of writing things down and, you know, having experience every day. So you arrive to a farm and you start your record. You know, at 9 o'clock you get fed and you make sure that you see that the other turkeys are well fed, and you know, you have ample time and leisure. And as time goes on, yeah, first maybe you are not very confident. I mean, it's your first observation, so what if this is random and what's something bad gonna happen? Second day is the same, third day is the same, fifth, you know, and eventually when you get to your months, you know, you get quite comfortably set in your ways of observations, and then you've accumulated you know, 300, say 366, fine, on the other example, 1,000 days of, you know, 999 days, 1,000 days of exceptionally good, well calibrated observations that your life is good, your farmer loves you, and made these observations in the wide variety of circumstances, Wednesdays, Thursdays, and rainy days, warm days, anything. Each day you add to your observation count, say at each at every circumstance, irrespective of the outside situation, you are still well fed and farmer takes care of you. However, what you don't know, that Thanksgiving is right around the corner, or in the case of a lamb, the Eid al-Adha festival is around the corner, and then suddenly that day comes and your throat is cut. So boom, the experience of a big surprise and your death, right? So now what it does, unlike the pure problem of the induction, which sort of deals with truths that don't depend on the observer, here, you know, this Thanksgiving turkey problem actually puts the observer right in the middle of the induction problem. So here, this is quite important to say the true problem of the induction sort of tells you that it's actually kind of illogical to use inductive reasoning It is irrational, rather, sorry, not logical. And it's hard to logically justify a conclusion based just on experience. In case of science, that would be basing things on benchmarking over the previous data sets, and saying, well, that is absolutely true. Well, that's why it's probability, not truth, right? And remember, science is not verifiable completely, yeah? So you can't really verify things, absolute certainty. However, what you have to do is practically assume some inductivity for life to function. Yeah. So you have to say, well, if elevator, I'm living somewhere, and elevator works today, I live in that flat, right? And therefore it will work tomorrow. I have to assume that it may break, but if I don't assume that, there's basically no order and it's chaos. Yeah. But yeah, while is it necessary to live our lives based on that inductive reasoning, it's important to recognize that this is not 100% verifiable, and indeed, your experience will be wrong, and elevator will break that day and it won't work, right? Eventually, that's going to happen, right? You just don't know when. So what to do? Would you continue searching for best explanations? Well, that's why the observation of the purely detached observation of, okay, I falsify the observation eventually that sun doesn't rise tomorrow. Maybe okay, fine. But when you're in the middle of that, that is inviting. You're going to be hurt by this, and that's why suddenly this problems from this turns into a kind of real life situation problem. So you leave aside the deductive reasoning, which doesn't really tell you much, doesn't really help you with anything beyond learning Greek philosophy in my mind. But inductive and abductive reasonings, which is just sort of in search for best explanation, it doesn't give you certainty, and then you may get no verification eventually, right? And you verify it, and then boom, you don't verify it. And when you don't verify, well, you get an event, right? And that event could be survivable, okay, but it may not be survivable, and then you'll end up with a catastrophic black swan. And then there are two options: you perish, right? So that means when the observer perishes, no one really to look at the inductive reasoning anymore, or you build a resilience, or what's more, resilience is about minimizing the downside of the negative events. What Nassim Taleb also proposed, you would just not survive the crisis, but also position to benefit from it, knowing that you'll have to spread your bets and never actually believe the experience. And this is where science is not going to give you the answers, because the science is not going to tell you that what you should do. Science it's an instrument. And this is where we're going to talk about how science is an instrument here, and then we'll come back to human affairs once again. So let's talk about scientific method, and scientific method is truly what it is. Science is a method. Science is not truth. Science, it's not something that is tells you absolute certainties. For sure, it doesn't tell you absolute certainties. Is a method. Sometimes scientists are not very truthful to that, which is very understandable, because we work in there, and scientists are human, but science is a method, right? And you'll have to kind of look at the various stages of that process. Then it'll probably be easier for us to recognize in what science truly is, right? So let's look at scientific method definitions. A simple definition of explanation, it's an attempt to formally explain something easily. It is not really building a theory yet, it's just a simple explanation. When you go to a theory, then it gives you a more general explanation of underlying nature of phenomena. You start connecting the dots, but you get a hypothesis from a theory, and it's a hypothesis then formulates a prediction that is relatively precise, and it also gives an opportunity to test it. So once the hypothesis is tested, You can say, well, could it be verifiable or not? And then the scientific method, therefore, built from hypothesis is the systematic and empirical, empirical through the test, investigation of the world through observation, experiments and measurements. And then you can reformulate theories. You also have to propose alternative hypotheses, alternative theories, models in parallel to the one that you currently have. Sometimes it's called null hypothesis when it's kind of an opposite of the hypothesis you have. So step would be first, you'll have to define a question. Define what is it that you're wanting to answer, yeah? And then you have to gather information and resources, you observe it. So in terms of data, you start looking at data and you said, okay, now I'm remember the discussion about the data and knowledge. So then you'll start still not knowledge, right? It's just that you gathering the information and observing it and starting once it's data into some sort of a describable form, that's information. Then you'll have to form an explanatory hypothesis to explain the information that you received from various sources and link it together. And then you'll have to test hypothesis, and you'll be tested by performing an experiment. If it's an experimental science, you would also be looking at other factors. Say if you propose something on this data set, on this data set, then you use another one, and then you say, well, how does that match with this one, and does that theory hold true? Say in a world where I work, say in geology, the testing would be say by finding another outcrop far away from when you believed that you know uh, from one area, and say, well, actually that is geological description of that area is true. You can even drill a well and then find out that, okay, the well um, tested your uh, theory, and the well found oil and gas. So that means that if the well been found, that's basically a test of a theory. And so you build a theory, you build an testable explanation, you drill it. If you failed, you falsified it, and it was wrong. So your theory was wrong. So you build another one. That's another thing that sometimes it's hard to understand, um, because business is not science. That it is not wrong necessarily not to find something. It's just the theory that you have first built has not taken, has been falsified because it didn't really take account of all information. It's very difficult to not falsify something. Eventually, it will be falsified. So okay, and then you get back, you test hypothesis and collect data in a reproducible manner. So you get the data, then you reformulate the theory, you analyze the data, and then interpret it and draw the conclusions. And then say if you falsified it, and then there's a new hypothesis starting out from that. Of course, then you get the published results and peer review them in journals, and this is if we're talking about science and retest. And other people would say, well, I don't believe what you found. Okay, let me retest what you have, and things like that work together. So now, I have to say that this such description have a little relation to the ways things are practiced, because scientists are not science, and a lot of that biases remain. And would now you'd have uh, in a testable sciences, say, frequent things like drug tests and so on. It happens a lot, and you strive as much as you can, but the problem of non-verification in science is very big. Simply impossible to verify all thousands of tests that happen in various fields. And I think the other big item we'll talk about is the confirmation bias, that you publish on the results that actually show positive results, and you don't publish what's showed negative results. So you actually bury all that data, and that data doesn't exist. And so obviously there's a huge bias in all the publications, which I think is being addressed at the moment, but we'll talk about it later. Let's talk about what is science and what is non-science, pseudoscience, and then I actually not being derogatory when I say pseudoscience. It's just that you'll have to be able to distinguish what is the scientific method, which is really careful collection of um, measurements. Pseudosciences don't require that because they would have relatively fixed ideas. You don't necessarily have to have peer review, you don't have peer reviews at all. And a lot of this then hides in the conspiracy theories world. Obviously, you will basically take one result and fit almost like an explanation to it. The critical thing between the pseudoscience and science that things are basically non-falsifiable in pseudoscience because any explanation that any new data that comes along can be fitted. The classical example here are pronouncements of uh, some sort of vague pronouncements of predictions like Nostradamus or Vanga or any other of those famous soothsayers. I forgot the name of those the people, right? That predict the future, right? Almost any world event like with COVID, today and so on could be fit into the wording and sayings of the people, and it's almost impossible to actually falsify this. And scientific measurements are usually tabulated and showing various correlations, regressions, and they usually set certain settings. Yeah. However, the non-scientists or pseudoscientists obviously hide all these kinds of measurements or create black boxes, and it's just very difficult for to be able to test the hypothesis or so-called pseudoscience hypothesis. So some of the I mean, clearly the line is a little blurred, but in case of clinical psychology, say it probably is science. If you talk about the non-verifiable things like consciousness, um, some of it is science, but some of it is still not science. And religion, clearly not science. Nothing wrong with that. It's just, as I said, things based on belief are not necessarily testable, and therefore they're not scientific. Yeah, that's nothing wrong with that. It's just we have to say what is science, and that actually is helpful for non-scientists to understand that science is not truth. Science is a method to get to the best explanation within the probabilities. And the person who said it the most is the famous Austrian philosopher of science, Karl Popper. Um, he is kind of so you say a matter or uh, the big guy of scientific method, right? What he believed that the criteria of scientific status of a theory is falsifiability for that. Of that, he didn't believe in absolute truth. He couldn't really believe in it because he knew that inductive logic is not really demonstrating truth, right? So a theory idea shouldn't be scientific unless it could be proven false on principle. So classical examples. I mean, there's a number of the examples we talked about black swan, but there's a number of scientific explanations that have proven to be not true and demonstrated and falsified. So real science aims to be disproven and it shouldn't be confirmed. It's very difficult because it kind of goes against the human nature to confirm the principles that you hold dear. And the more you get confirmation, the more you get accustomed to idea that this idea is probably best. I mean, right now you can see it with some of the um, well-established theories of that amassed so much explanation you wouldn't really believe that it could be wrong, like the Darwin's theory of natural selection or Einstein's theory of relativity, or right now with climate change. There's no possibility in your mind that things like that could be wrong, but they could be. Who knows? Who knows what comes in the future and refutes those ideas? And I just can't uh, remove that possibility I don't know, you're probably very minuscule, but it could happen. And some of the theories get refuted every time, quite frequently. So he advised scientists to try to falsify hypotheses, to search and test the experiments that seem most doubtful. And what's said, basically, even a large number of successful confirmations are not convincing. And you have to make the tests that actually could disprove it, but do it obviously with a scientific rigor. Now, we'll deal with probabilities. So I'll come back to the probabilities again. So inductive arguments, theories, explanation, and scientific method itself always is a matter of probability rather than certainty. Yeah. So the question is, what defines the standards of that proof? Because you can't go to 100%, right? So when you say that something is acceptable, meaning that you will not accept something as true if that standard is not met. So, I give you an example here. Say I invented an app that allows you to predict the outcome of a coin toss. Yeah. So I'll come to you and say, hey, I'm going to coin toss you, and I'll tell you what it is. And you believe me. And if I would be able to predict it using this app, you will buy it from me, right? It's a great magical, there's an example in the book I'm using, but I think it's a brilliant one. So what you say, okay, so let's toss a coin. So if I toss a coin once, I get a 1 in 2 chance that it's just a pure random coincidence that I get a good answer. So it's 50%. Would you believe me then? Probably not. Then I toss it 2 times. Then it's 1 in 4, so it's still quite substantial. 3 times, that's 12%. And then I toss it 4 times, and say if I predict 4 times in a row, now it's a chance of 1 in 16, so I got 6% chance that it's through luck, right? So now I get this statistical significance thing. Is it possible that this is actually something which is statistically significant and could be a standard of proof? It's a probability that particular result is achieved by entirely chance, as opposed to having some sort of a cause. Right now, I'm sort of getting to an idea that it's a threshold here, and the threshold is the significance usual way of establishing that standard of proof, and that happens in experiments where you run them one and again. In this case of geology, say you collect samples more and more times, and then test the samples many times rather than one times. And the more things you test, the more samples you test, the better the that statistical significance is. They call it p-value, which just means probability value. And something is statistically significant if results you're looking for exceed that p-value. So say, it's 95% confidence. So it gives you confidence here, right? So the coin toss of 5-6 times, now I'm getting to a chance of it being through luck at 3 to 5%. So it's above the 95% threshold. So if I did it 5 times, I would be above that. Yeah, cool. And so let's say you get a probability of observations. You toss the coin, yeah, and then you will, you kind of distribute the, in case of 1 to 2, so it'll probably be something like, well, I got 50%, and that sort of there you end up with 95% statistical threshold, and you'll get your observed p-value. In that case, it's obviously 4%, and then so if whatever 5 times 5 coin tosses. Now it is actually possible in that case that I still have random. I haven't eliminated the random nature then, and maybe I need to do 1,000 times, right? 1,000 times you get to 0.1%. But is it still possible that I'm random and this app is wrong? Yes, it is possible. And that is why this is kind of the tricksters operate. Say, people would say come to a large number of people and test the same thing. And for somebody, it might be 10 times in a row. And 10 times in a row means that you'll actually have 1 in 1,000 chance. But it doesn't really mean it's 100% truth. It just means that it exceeded 95% confidence. So here is the difference between exceeding the 95% confidence, that is a standard of proof, and being 100% truth. I think that's a kind of an exact situation that you should understand. So these observations do not tell you the truth. They tell you the likelihood of, or the confidence level. But just like I told you with those tricksters, someone, repeating that experiment many, many times can achieve, um, having achieved sort of coin toss and getting heads 10 times in a row and exceeding your p-value, and you will accept it. But it's just pure luck. So, just sort of humble, try to be humble here. And the another kind of reason to be humble is thing called correlation does not mean causation. That phrase refers to inability to deduce cause and effect between two events, and solely on based of just observable association. That's why you employ again that critical thinking we're talking about. So, correlation with two trends follow each other closely. The exact degree, you can build a, coefficient of how the coefficient between them. And causation, there's an assertion that one thing direct cause of another. So, for example, take an ice cream sales in US and shark attacks. And boom, both ice cream sales and the shark attacks increase when, in July. It increases when weather is hot. So does ice cream sales cause shark attacks, or maybe shark attacks cause the ice cream sales? Well, it's not obviously logically it's sort of there, but it's wrong. Obviously that none of them, they're not exactly related. But there is actually a third factor, and it happens when the weather is hot and sunny. They're not caused by each other. They're caused by good weather. Lots of people go on the beach and then get bitten by shark, and they have to swim in the sea. And when they swim in the sea, they get attacked by sharks. Hey, presto, there is an explanation. So I can't prove that there's a causal link, but I strongly suggest that there are other explanations for these things that exist. And very easy to find millions and millions of highly correlated things. If you browse on the internet right now, you find lots and lots of completely unrelated things that are related. So for instance, here on the right, there's a correlation between the number of suicides in the US and um, spending on science and technology, and they are highly correlatable. But is there any way these are correlated? Do they even have that third factor? I doubt it. I mean, third factor is a good explanation in the first one. There's other things when you kind of mix cause and effect, do some statistical manipulation. It's possible that these dots have been manipulated, but I think the most likely explanation is pure chance. And that kind of explains lots of these correlation causation things because of the sheer availability of data. You can make almost any prediction. So immediately, you can say, well, that is not a relevant example. I mean, it's obviously a joke example, but it's not joke all the time, because there are some serious things that happen there. I mean, especially in markets, people do it all the time. They link, one event to another. They link, boom and bust cycles to oil and gas prices. Then, people make professions out of these things. And I think Hassan Nassim Taleb and, the authors of the Radical Uncertainty book tell you that, you know, we're not sure about validity of those professions, especially when they deal with highly certain parameters. So not only that you have to do a correlation causation, employ logic, you also have to understand how certain factors related to other factors. And that's why things are quite more difficult. In the next series, we'll still continue this interesting topic, the next lecture, and we'll continue this topic and maybe touch more on scientific method and generally cover lots of more things on critical thinking. There's still a lot more to cover. Thank you very much.